In this video, we're going to talk about functions. Let's start with the basics of function. So what is a function? So a function consists of a set of inputs, a set of outputs, and a rule for assigning each input to exactly one output. So the input part of the function is called the domain. So we can just put it down right here that the input is called the domain of the function. And the set of the output of the function is called the range of the function. So the output part of the function is called the range of the function, right? So let's consider some example here. So let's say we have a function where the domain is a set of all real numbers. So what is the domain here? The domain is the input. So the function input contains a set of all real numbers, and the rule is to square the input. So then, if you have something like that, let's say x is equal to 3, and x here is representing the input of the function, right? So the rule is saying that we should square the input. So how do we get the output of this? So we are going to square the 3 to get 9. So the 9 right here is the output, which is the range that I was talking about, right? So since every non-negative real number has a real value square root, now every non-negative number is an element of the range of this function that I just spoke about here, right? So since there is no real number with a square that is negative, the negative real numbers are not elements of the range. So we can conclude from this that the range is the set of non-negative real numbers. If you get that. So for a general function with a domain D, we often use x as the input. So x is usually represented with input, and the y represents the output. That's what we normally designate to what function. So when doing we often refer to x as independent variable. So x is normally referred as the independent variable, right? And y is represents the dependent variable. Now why do we associate y to be dependent variable, or why do we refer a y to be a dependent variable? Now this is because we know that y depends on x. That's why it is dependent variable. Now, so using the function notation, y should be equal to f into bracket x. Now, we can read this as equation as y equals to f of x. So this is equal to, so y is equal to f of x. That's how we read it. So y is equal to f of x. So for squaring, for the function we described earlier on, the example that I used earlier on, that we have a function of all real numbers where we presented the input to be 3 right here, and the output we need to square. How do we write this in the function from using this equation right here? So with this one, we can write it as f of x should be equal to x squared. That's how we can write it. Now let's look at some visualizations here, right? The first visualization is if I have this as a function. So let me write this a function right here, right? So we have what goes into it as x, which is the input, and we have what comes out to be the output, which is the f of x, sometimes y, right? So this function can be visualized as input output the device. That's how we do it. Now let's look at another visualization here. So let's say we have 1, 2, 3, 4, and we have another set here which is 2, 4, 6, right, and let's draw an arrow here. This arrow is f, which is the function, right? So let's mark maybe 1 to 6 and 2 to 4, then 3 to 2, then 4 also to 2 right here, and see something now. A function maps every element in the domain to exactly one element in the range. So although each input can be sent to only one output, two different input can be sent to the same output. So that's why we have 3 and 4 matching to 2 right here. So the same number in the we have two different number in the input side matching to the same number in the output side. That's how we can do it. We cannot match 2 matching to both. Maybe we have 2, which is 2 itself is matching to let's say, how do I even put it? Okay, let's say 1, which is matching to 2, and the same 1 is matching to 4. It cannot happen like that, but we have a different number in the output side matching to the same number in the output side. That's what I'm talking about here. Now let's look at another visualization here. So let's say I have this like a graph right here. We have the x and we have the y, and the y sometimes f of x, right, in the function form. Let's say here is 2, then we have 0, 2, we have 4, there it goes. So we know that the y part is the f of x part is dependent variable, and the x part is independent variable. And we know the x-axis is there. So we know the x-axis is the domain. So the x-axis is the domain. And as you can see, the x is 1, 2, 3. That it goes on like that, right? And we have the range right here to be the y-axis, right? Which is 1, 2 right there, right? So let's say we are plotting that. So we have 2, then 1. So let me say 1 is here. So I'll plot to 1 and 2, then 2 and 1 right here, right? So with this one, how do we put it? So we can write it as 1 comma f of 1, which is equal to 1, 2. That's how we can write it. Then with this one, we can also put it as 2 comma f of 2, which is equal to 2 comma 1, right? So something like that is very, very simple to do, right? So in this case, a graph of a function f has a domain of 1, 2, right, 3, which I didn't just put it on the graph right here, and the range of 1 and 2. So the independent variable is x and the dependent variable is y. Very, very easy to do right here. So we can also visualize a function by plotting which is the x and y in a coordinate plane, where we have y to be equal to f of x, right? So the graph of a function is the set of all these points that I just plotted right here. For example, we can consider the function where the domain that we just wrote right here, this is 1, 2, and 3, and it's having the rule of f of x. What we just did here have the rule of f of x to be 3 minus x, right, of this graph that we just did here. So it's very, very easy to do, right? So we have to take note of these things right here. Now, every function has a domain. However, sometimes a function is described by an equation, as seen maybe you have f of x to be equal to x squared. Now, with a specific domain given. So in this case, what we are supposed to do is that the domain is taken to be the set of all real numbers x, right? For which f of x is a real number, right? So, for example, let me give an example here. Since any real number can be squared, if no other domain is specified, we consider the domain of f of x, right, to be the set of all real numbers. So on the other hand, the square root function of, let's say, the square root function f of x root x only gives real output if x is non-negative. So therefore, the domain of the function f of x equal to the square root of x right here is a set of non-negative real numbers, so sometimes called the natural domain, right? So let's give an example here. So for the function f of x, which I just did, which is equal to x squared, and the function of f of x equal to root x, right? The domains are set with infinite number of elements. So clearly, we cannot list all these elements. So when describing a set with an infinite number of elements, it is often helpful to use set builder notation interval, right? So using the set builder notation to describe a subset of all real numbers denoted by the R sign. So we use this to denote that. We can write it as the x, then cross this line, then x has some property. Let me write it this way, some property right there. So we read this as the set of real numbers x such that x has some property. For example, if we're interested in the set of real numbers that are greater than 1 but less than 5, we could denote this set using set builder notation by writing that x is such that 1 is less than x less than 5. That's how we can write it. So a set such as this, which contains all numbers greater than a and less than b, can be denoted using the interval notation as a, b. So therefore 1, 5 is equal to x such that 1 less than x less than 5, right? So the numbers 1 and 5 are called the endpoint of this set here. So if we want to consider the set that includes the endpoint, we will denote this by writing with this one, not the bracket one, not the bracket, right? But with this one, so 1, 5, then it should be equal to x such that 1 less than or equal to x less than or equal to 5. That's how we can write it. So we use similar notation if we want to include one of the endpoints but not the other. So with this one, to denote the set of non-negative real numbers, we could use the set builder notation as which is x such that 0 less than or equal to x. This is how we can denote that. And for the smallest number in this set is 0, but this set does not have a large number, as you can see from there. So using the interval notation, we use the symbol infinity, which is something like this, right? Which we refers to as the positive infinity, and we could write it the set notation builder as 0, right, comma, the infinity sign, then close bracket, which should be equal to x such that 0 less than or equal to x, right there. So it is very, very important to note that the infinity sign, which is there, this one that I just draw here, is not a real number. It's not a real number. So this is not a real number. It's not a real number. Right, so it is used symbolically here to just indicate that this set includes all real numbers greater than or equal to 0. Right, so similarly, we wanted to just describe the set of all non-positive numbers. We could just write it as negative infinity comma 0, then with this bracket should be equal to x, such that x should be less than or equal to 0. Then you close it, right? Then you close it. So here the notation negative, the notation which is the negative infinity here refers to the negative infinity here, right? So it indicates that we are including all numbers less than or equal to 0, no matter how small it is. So the set also which is which is negative infinity, then positive infinity, can also be written as x, such that x is any real number, like this, which refers to the set of all real numbers. So some functions are defined using different equations for different part of their domain. So this type of functions are known as the piecewise defined functions. For example, suppose we want to define a function with the domain that is the set of all real numbers, such that f of x should be equal to 3x plus 1 for x greater than or equal to 2, and also a function of f of x which should be equal to maybe x squared for x less than 2. We can denote these functions or function by writing f of x should be equal to, with the big bracket here, or the curly bracket here, which is 3x plus 1, then x squared, where we have here to be x greater than or equal to 2. Then with this one we have x less than 2, right? So when evaluating this function for an output, which is the x, the equation to use depends on whether x is greater than or equal to 2 or x is less than 2. For example, since 5 here is greater than 2, we can use the fact that f of x, which is equal to 3x plus 1 for x less than greater than or equal to 2, and we will see that when we put the 5 inside the f of x, which is f of 5 right here, then we will have maybe 3 times 5 plus 1, we will get 16. So on the other hand, for x equal to -1, we can use the fact that f of x equal to x squared for x less than 2, and we will see that when we have f of -1, we will get 1, right? So this is the end of the basics. So this is just, we are just covering the basics of function right here. In our next video, we'll talk about examples of function. Examples, we will deal with the functions. What we just talk about in this video, we will solve some examples, real examples, for you to understand it very, very well. So this is just some basics of functions that you need to just understand, right? And thank you for watching this video. I'll see you in my next video.